Good evening, sir. Shall we start the session? Sir?
I'm audible, no?
Yes, sir. Now it's audible.
Okay, madam.
Okay, sir. We shall start the session.
Yeah, okay, madam. Okay, thank you.
Good evening to all the participants and those present here. So it is with great pleasure that we extend a warm welcome to our esteemed speaker, Dr. Arun Dominic, Assistant Professor, Department of Electrical and Electronics Engineering at NIT Surathkal. Dr. Arun Dominic is Assistant Professor at NIT Surathkal with over 5 years of experience in academia and research. He holds a PhD in electrical drives from the Indian Institute of Technology, Roorkee, and an ME in Power Electronics and Drives from Anna University, Chennai, and BE in Electrical and Electronics Engineering from Anna University. With his impressive academic background and extensive research experience in electronics and electrical drives, he has been making remarkable contributions to the field, particularly in fault tolerance control and power conversion strategies for large electric drives. Since joining NIT Surathkal in 2019, Dr. Arun Dominic has been actively involved in teaching, mentoring students, and conducting research in power electronics and motor drive systems. With expertise in high-performance drive systems, power conversion, and control strategies, his work contributes to improving the reliability and efficiency of industrial and commercial electrical applications. Through his academic and research endeavors, Dr. Arun Dominic continues to play a key role in enhancing innovations for electronics and drive technologies. On behalf of everyone present here, I extend a heartfelt welcome to Dr. Arun Dominic and look forward to an engaging and enlightening session. Thank you for being with us today, sir. We welcome you.
Thank you, madam. Shall I start?
Yes, sir. We can start.
Thank you very much for the brief introduction. So, in this today's topic is emerging technologies in renewable energy systems. So, there are a lot of methods for power generation. Like if you see, there are wind power, hydroelectric power generations, and for that, in some cases, thermal power generations. So, they use certain inputs as coal or other fossil fuels, where it leads to pollution, and once it is utilized, we cannot use those materials. So, because of pollution, there is the global warming is there. So, what the entire research community has decided at those days itself, so to go for a renewable energy systems. So the renewable energy systems is broadly, you can say it is classified into solar, wind energy systems, and then green hydrogen, and there are hydropower, geothermal, and marine energy. In my presentation, I'll be giving a detailed introduction about the solar energy, wind energy, and a little bit hydropower energy. Okay. So, if you see, as I mentioned earlier, there are different renewable energies, technologies are there. So, what we know mostly solar energy and wind energy. The latest one is that geothermal, biomass, and tidal energy. Okay. So, the main advantage of the renewable energy system is, particularly solar and wind energy system, the pollution is less, as well as the energy can be renewable, so that we can use for further for our power generation also. Okay. The first and foremost thing is the if you see here, And also the main thing is that nowadays the demand for electrical energy is also increased. So if you see, the government is forcing or pushing us towards the renewable energy resources and renewable energy power generation, since we have the resource for the production of electrical power through renewable energy. So if you see in the slide, I can say um, it has reduced emission. In other words, you can say which has less pollution, and even that the global warming is also reduced. So that is why if you see the uh, government of India, see here if you see the government of India is having a national electricity plan that is framed by the Ministry of Power with the aim to urbanize the complete India in a electrical, what you can say, there is no power loss. So for that, they have devised a plan of action that in the year up to 2047, they want to increase the solar power generation up to 750 gigawatts, and there are good potential for the wind power. So wind power potential is good, and they have decided to increase the wind power generation up to 400 410 gigawatts. Okay, so as of now if you see, there are, for example, 175 gigawatts power of renewable energy we are getting. So from most of the renewable power we received from 100 gigawatts from solar and 60 gigawatts from wind, and remaining other 10 gigawatts from biogas and 5 gigawatts from the small hydro power plant. So as far as our Indian scenario, we want to increase our power production to 750 gigawatts in the year 2047. So if you see here, the global needs is also increasing. So if you see in the global wise, if you see, most of the power production is done through coal. You can see here 36.4 percentage of power is generated through the coal as an input. Similarly, 23.2 percentage as a natural gas. Then 15.2 percentage of hydropower and 9.1 percentage of nuclear power. Only 7.1 percentage of wind energy and 4.0 percentage of solar power. So if you see this coal, natural gas, they create a lot of environmental pollution, and as a result, our Earth, the global warming is happening, and it is a biggest issue nowadays that leads to the climatic change all over the world. So the entire research community have decided that to increase the pollution-less renewable energy resources, like particularly the solar and wind energy, so that they can reduce the power generation through the coal and natural gas and other um, means of power generation where more pollution is there. So if you see the overall the plan for the world, that they want to increase this wind to 200 times the existing power generation through other means. Similarly, solar also they have decided to increase a lot. So if you see, there is a good amount of that is good potential is also there, as well as there is a good demand for power through this renewable energy resources is also there. Okay. Yeah. So now if you see, what are the challenges in the renewable energy adaptation? So we speak renewable energy, everything, but what real challenges we are facing. So if you see, for installing this a solar cell, the
Excuse me,
initial
sir.
hello.
Sir, your PPT is not moving.
Oh. Now it's moving.
Yes, sir. Yes, sir. And the sound, some distractions is also there.
Now it's okay.
No, sir. I think a fan sound or something.
No, I have switched off my fan. Now it's okay, madam.
It's okay, sir. It's now okay.
Okay,
Sir.
okay.
Thank
Thanks,
you.
madam. Thanks. Yeah, you can say at any time if you face any issues.
Okay, sir. Thank you.
Okay, okay. So the real challenges what we face in this adaptation of renewable energy resources is, if you see, the case of a solar cell, for production of that solar cell, the initial the cost for the solar cell is very high, as well as bringing the fine particle of that silicon. It requires very advanced technologies. So that is one real challenging task in the renewable energy adaptation. And second, if you think that if you see a windmill, the land acquisition and installing the windmill itself, it requires a lot of uh, not only in terms of cost, in terms of technology, it is needed. For example, if you see, we are from a place, we are from Nagarkoil. If you see the place nearby Nagarkoil, a place called Pandal. It is the in Tamil Nadu, I suppose that is the highest production of wind power in Tamil Nadu. If you see, nearly 1,500 megawatt capacity of total capacity of the power production, total capacity of the windmills installed in that place will be roughly 1,200 to 1,500 megawatts can be generated. So that much power potential is there. So, but the problem is that land acquisition, then installing, and mainly the maintenance. Okay, once you put some money and if you install, but the maintenance is a very big thing. The control mechanism for controlling the windmill, still a lot of hidden things are there which where we the people are facing a lot of challenges. So these things are these things are challenges to in implementing the renewable energy. And also, as far as if you see the government is, if you concern, so they need a proper policy and proper infrastructure development for implementing these renewable energy systems. Okay, so this is an overview of that renewable energy systems. So here, what is the future prospects of this renewable energy system is? So they, as I told earlier, as far as government's now for 2047, so they want to expand the wind and solar energy capacity. So that is increased power production up to 170 gigawatts, as I explained in the previous slides. And the second one is the advancement in the battery storage and smart grid. So we all speak smart grids, how it is advantages, everything we are speaking nowadays. So we want advancement in those technologies also. We want to get a pure power with reduced harmonics. Once we are using the power electronics, we may get harmonics. So we need to have reduced harmonics or a pure harmonics less power production if it is possible. That is needed for us. And third, there's a new technology called growth of green hydrogen technology. That means it is a different new technology where splitting hydrogen and oxygen from the water, and from there they are generating. So it's a new it's a technology, and government is also seeking investors to invest in this technology and to generate more power so that the at least to some extent the generated power can be satisfied the demand, the rising demands. So government was trying to increase the investment and it will bring new policies later stages. And here, apart from this, the role of power electronics. As a power electronics engineer, power electronics plays a wide role nowadays in any electrical equipments. If you see coming to your houses, you have an inverter. So it's a DC to AC converter. I can say, as far as the solar cell, we are using DC converters. So DC converters, if you see, there are different topologies are there. Like in broad ways, I can say, if you classify it as an non-isolated converter and an isolated converters. Like non-isolated, if you see buck boost, choke, sepik, theta, etc. So other converters like isolated converters, you can see forward converter, full bridge converter, and dual active bridge, phase shift, full bridge, etc. A lot of converters are there. So different converters will be useful for our different applications, and designing those converters, it is not it is a really challenging task to get the desired performance. For example, if you see, if you design a converter for a low capacity, like 100 watts, that...
Excuse me, sir. The slides are not moving again.
Yeah, now it's moving, no, madam?
No, sir. So slideshow, put it in the slideshow mode, sir.
Slideshow. I'm sharing the slide, no problem, no? Okay, okay. Now it's okay, no? Now it's okay, no? Okay, thank you. Yeah, okay. Now it's okay, no?
Yes, sir.
Yeah, thank you, madam. So there are a lot of challenges for them. Like for example, if for a converter with 100 watts, it has separate design. And apart from that, if you go for your converter of 1 kilowatt, it has certain challenges. Even for designing, implementation, it has a lot of challenges. And nowadays, the most important challenges is that by implementing the control algorithm for the converter. So that is a key challenges are also there. Okay, so that also has to be taken into consideration. Okay, so as I told, power electronics field, it is applied each and everywhere. Okay. In other words, if I want to say, without power electronics now, there is no electrical equipment. Most of the equipment will be employed with the power technology. So to be a well expertised in power electronics, we need to know, for example, if you take any power semiconductor switches, let me take a power MOSFET. So to give pulses to the gate of the power MOSFET, we need to know how to generate the pulses. In olden days, they generated through the analog circuits, or they may have a regulator ICs for generating the pulses. But however, control in those ICs is difficult. So they have gone for a digital implementation. Like if you see, we can design our own algorithm and we can implement in the control card. For example, you have a DSP processor. It is based upon the sampling of the signals. It works for you. We can change the sampling time and we can vary the frequencies, everything digitally by the help of this controller. So here it can be a microcontroller, it can be an digital signal processor, or it can be an FPGA processor. There are a lot of processors available in the market. So overall, if you see, and apart from that, if you want to
if you want to implement your power electronics in drives, you should be also good in machines and electrical drives. Power electronics field nowadays, without power electronics, electrical, it's very difficult to control the system. Okay, so the figure which I have showed here is, you can see, if I want to get a different output, for example, in a DC converter, irrespective of variation of the input, you are giving a variable DC and you want to get a constant DC output, so there should be a closed loop. So closed loop control, we are going to implement our control algorithm, and from that control algorithm we will generate the based upon the control algorithm we will generate the pulses, that is pulse width modulation, PWM pulses, then it will be given to the gate of our power conductor device, power master. So a closed loop operation is important. So we always want to get a different output voltage irrespective of variation in input. So closed loop control is necessary. In the closed loop control is there are inner current control is there and outer voltage control is there. So if you go for an electrical machine also, you have an inner current control and outer speed control. So first we have to define the inner current control loop and the outer current control loop. Okay, the inner current control loop will be a fast loop, and outer current control, outer voltage control will be a slow loop. First we have to define current control, then we have to go for voltage control, and then so once this
Sir,
can be implemented. Hello,
sir, again, it's not moving, sir. That slides are not moving, and voice disturbance is there.
there.
Yes, sir.
Now it's okay, madam.
No, it's not moving, sir.
Now you can hear me properly.
No, when you're talking, we are hearing the disturbance.
Now it's not clear.
Normally it's okay. When you're talking, the disturbance is hearing.
Can you give me? I'll change my. Can I change my mic and?
Sir, sir.
Can I change my mic?
Okay, sir. Okay, and the slides are also not moving, sir.
Okay, just a minute. I'll change my mic.
Okay. Sir, you are not audible, sir. Not audible.
Am I audible now?
Yes, sir. Yes, sir. Now the voice is clear.
Okay, madam. Thank you.
Okay, sir.
So now you can see the screen, no?
Yes, sir. Yes, sir.
Okay, thank you. So sorry for the disturbance because there are some bandwidth issues there. That's the reason.
Okay, okay, sir. No problem.
Sorry for the interruption. So as I told, like if you are designing a converter for 100 watts, and they were designing a converter for 1 kilowatts.
Sir,
There's a lot
the
of
PPT is not open, sir.
PPT is moving, no?
No, it's not visible.
I think now it will be visible. I think. Yes, madam.
Yes, sir. Yes, sir.
Okay, fine. Now it's completely visible, no? My slides.
Yes, sir.
Okay. Thank you, madam. Thanks a lot. So there are different even converter that design itself. A lot of difference are there, and nowadays we have to take care of EMI, EMC issues. Once so these things have to be addressed in the power electronics as far as DC-DC converters are concerned. And here, if you see, like in a broad sense, if I want to say the power electronics application, as I told, even it is used in nowadays aircrafts, ships, in all this traction applications. Apart from the traction applications, even in our day-to-day life, in UPS, we are using this power electronics, other consumer electronics, load, modern refrigerator, etc. Even if you see now the air conditioning system, which is coming with inverter based. So that much technology we have improved Similarly, if you see in industries, in case of a motor drives, we are using power electronics. Okay, so for controlling of the solar or for maximum power point tracking, we need power electronic system. So solar energy is a basic solar energy principle is that it converts the um, sunlight into its electrical power. Okay, so we install a solar cell in our rooftops. So there it is converted into DC bus converters we have. It is solar light is converted into DC. Then DC to DC converter is used. From there, DC to AC conversion is done by an inverter. From that inverter, we are stepping up the voltage and connecting it to the grid. So this is the basic curve for voltage and the voltage, current, and power curve. So you can see the maximum power we have obtained at this point. So based upon that, we can that is peak load will get more power. That is more sunlight is there, will get more power. These things are there. Okay. So if you see the A curve, it's a curve drawn between current and voltage. If you see the maximum power point, this is the maximum power point tracking. Okay. So what is the power? Everything it is given for various voltage. Here, if you see nowadays in the solar PV technology, the solar, so there are different types of solar materials are there. That is, one is the crystalline silicon solar cell, and this cell is more. I'm audible now.
Sir, you're audible, but the slides are not moving. So you put it in the slideshow mode, sir.
Yes, madam. This is slideshow mode only. Now we can see, no?
We can see, but when you're moving into your presentation, the slides are not moving.
Okay, I think because of some bandwidth issue is here. That may be the problem.
Okay, sir.
It's very slow actually. Slow. It is moving very slow, I think. Am I right?
Okay. Okay, sir.
Yeah. So mostly we are using this crystalline silicon solar cell. So it has high efficiency and a long lifespan. In this, there are different other variants are there. So monocrystalline silicon and polycrystalline silicon. If you see the overall, the one drawback with the solar PV cell is that the efficiency is poor in compared to other method of power generation. So if you see the efficiency is 18 to 23% for a monocrystalline silicon, whereas for a polycrystalline silicon, similarly it is 14 to 18%. Okay, so thing is that these are all having high cost and performance is also poor. So some places we should avoid this and we should go for other type of solar cells. So there is other type of solar cell is thin film solar cell. So it is lightweighted, flexible, and cost effective. And then there are different types of materials. It is made up of amorphous silicon, cadmium, telluride, copper, indium, gallium, selenide. Different chemical combinations. These they are designed. So and also nowadays, if you see perovskite solar cells are there. So the efficiency comparing with this the old silicon, the solar cell, with this material, if you see the efficiency is greater than 24. Okay. So this is the, in case of designing of the solar cell, so they are going for this kind of materials in the solar cells. Efficiency is higher than the existing one. Okay, so you see this is a monocrystalline structure, and this is a polycrystalline structure, and this is a thin film structure of the solar cell. Okay. So if you see a comparison table, see this is the peroxide. So efficiency is approximately 25%, and the cost is also okay. medium wise, that is future in the rooftop and space, they will place the solar cell. Okay. And the next is that maximum power point. So we know very well is one of the most important thing in the solar power is maximum power point and maximum power point tracking. If you see, it is based upon that sun rays, how the sun rays is there. Based upon that, we can say how the maximum power point we can track it. So here, if you see, the graph is given between the maximum power point and duty cycle. That what does it mean, this duty cycle, and why I am putting this graph here means, if the converter will adjust the duty ratio. Since it is a DC-DC converters, we have a power electronic switches, the power MOSFET. So it adjusts its duty ratio so that we want to get the maximum power output. So if you see adjusting the duty ratio, we can get at this point we will get the maximum power. So this they have to do different calculations, and they have to find out at which place and which direction, if you give, the maximum power can be generated. Okay. And if you see the power electronics perspective, see, this is the solar cell. Here we have the photodiodes or sensor. Okay, so sensors are there. So what happens is output from this solar cell. Okay, so it is given to a DC-DC converter. From this DC-DC converter, so as I told, it can be any type of converter. Like normally, olden days they will use buck boost, and nowadays we have isolated converter. We have good isolation. And if you see, we are operating at very high switching frequency. So obviously, the size of the ICs or even transformer, if you see for this isolated converters, it will be operating at high switching frequency in terms of 20K. So the size is very small. So if you see the designing of the converter with the latest increase in switching frequency and with the latest like silicon carbide or other higher switching frequency switches once we use, the size is reduced and it is coming more and more compact. And the output from this DC-DC converter, the desired output, it is converted to an AC. And it, if you want, we can step up also if it is needed, and it can be connected to a grid or a load. Or else we can store it in the battery storage. So if we convert this, we can store in a battery. We can store this power in the battery storage. My slides are moving?
No, sir, no.
It's because of bandwidth issue.
Now we are seeing that. So from in the top, you go for the slideshow. You click
Here,
that slideshow. Top.
I'm sharing the complete screen.
Now it's not visible.
Now it's fine.
It's okay now, sir. But when you're moving forward, it is not moving.
Okay. I think because of bandwidth issues, it may be there, madam.
Okay, sir.
Okay. Yeah. So from this solar panel, okay, it is converted to now it's moving.
No, sir, no. So you continue, sir, no problem.
Okay, I'll share the slide later onwards.
Okay, sir, okay.
So here, the same, if you see the PV system, we have the power conditioning unit. and that means whatever the desired output power will get it from the output, and it is given to the energy distribution and whatever power it is needed. Okay. So here there are different types of PV component. That is, one is the without battery backup and with battery backup. If you see here, without battery backup, there is no battery storage. So PV cell, PV from the PV array, it is given to this power conditioning unit, and output from the power conditioning unit, it is given to the grid or the local load. Okay. Whereas in case of the power conditioning circuit, we are storing the power in the battery banks for some extent. So that is the one advantage with this battery storage. So in there also, in the PV cell, there are different power modules, and see in the second figure, if you see, there are different inverters for every power modules. Different inverters are connected, and finally it is combined and it's connected to the grid. This is one type of configuration. And the first figure, if you see, there are different power modules, and it is combined together with a central inverter, a single inverter, and it's connected to the grid. That is one type of the power inverter configuration. And the third one is that the string inverter is there. That is, every string, it is separately, it is connected to a different inverters and finally combined together and given to the grid. So there are a lot of research works are also going on here. Okay. So now, what are the challenges in implementing these converters? If you see here, once we connect a capacitor, that is earth parasitic capacitance, if we connect here, so there will be a leakage current will be flowing in this loop. So as a result of this, EMI, EMC, all those problems will come. So it will affect your converter. That is one issue. So other thing, if you see here, to overcome from this, there is an inverter called H-phase or Herrick power converter topology. So here, if you see, there is a switch they have put here. So that can be overcome. This one of the application of solar is that solar heating. The solar heating, if you see, on the top we have the solar cell, and the water gets heated. So it is like a closed loop. So here water gets heated and it is coming as an output to the outlet. So the reverse process is that it is cooled once again and is given back to this water given back to this pipes, and because of the solar, the pipes, this water gets heated and it is recycled. So this solar cells we can use for the solar water heating also. Next comes the wind energy. So wind energy, it is also one of the important renewable energy resources. So if you see the historically, it is one of the more than 3,000 years old this technology they have implemented. Although we know that within 2 centuries before, or long back itself, they have implemented it. Okay. So if you see the history records, in 7th century, they have implemented this in Persia, 12th century, they have implemented in England, etc., etc. It is there. So the main advantage of this wind energy is that, so there is no emission, so there is no pollution, etc. And the compared to the solar energy, the one advantage is that it is based upon the wind. So if there is night time, if there is no sunlight also, it can generate power. Okay, that is one important advantages comparison to the solar energy. So, but the problem is that we need to find out first where first identifying the proper place where the wind velocity is more. So that is one thing. Then other thing is that installation. It requires that if you want to install like a 1 megawatt generator, so it requires a lot of installation efforts you need to put. And the main the drawback is that we need to go for proper maintenance of this control system used in this wind power technology. And if you see the year of 2023, from last 13 years, throughout the global installed wind power capacity. So if you see, because of the advantages of zero pollution, so in the year last year, the power generated is more than 1,000 gigawatts. So this is a world status. So day by day, we are reducing the other like conventional power generation, and we are increasing the renewable energy techniques, particularly wind. We are increasing it. Okay, so if you see that the installed wind capacity is more in China. This is as far as 2023 status. So if you see in our India, mostly whatever I have shown here, this is peak. We are coming under as one of the peak regions of power generation. So this red color has 200 to 250 megawatts of power generation. So these things are given the red color. And in India, if you see the installed power capacity by state wise is Gujarat has highest power installed capacity, that is 12,000 megawatts, followed by next is Tamil Nadu and others. Okay. Coming back to this, what is the basic control system or the structure in this wind energy is? You can see this is the wind blades, turbine blades. It is connected to a generator. Okay, so then it is converted to AC to DC. Different cases are there, or AC to AC conversion will be there. This is for DC microgrid. If you see here, yeah, there are different technologies. Nowadays, they are using, as it shown in this, it's shown in this diagram. See this generator. What generator they are using nowadays is doubly fed induction generator. So olden days they were using a squirrel cage induction generator. Okay. So this squirrel cage induction generator, we need to have capacitor banks to act this induction machine to act as a generator. And also the problem with this squirrel cage induction generator is we want to design a converter with that capacity. Whereas in DFIG, if you see, only P by 3, that is whatever the actual power of that generator is there, P by 3 times the capacity we can generate, we can design the converter. So that is one advantage. And also back-to-back operation is possible. There are even subsynchronous operations possible, subsynchronous generator, subsynchronous motoring operation, super synchronous generator, super synchronous motoring operation is possible. So that is 4-quadrant operation of drives is possible with the help of a DFIG. So nowadays, if you see, mostly they are going for this and PMSM. Okay. So before that, what I will do, I will give some basic details about this windmills. So here, yaw control. So yaw control, if you see in that rotation of this blade, so which is called as angle control. So we have to control the angle. So for that, we say that as an yaw control, and yeah, there are other controls are there. So pitch angle control, yaw control. And in case of electrical control method, TSR control, optimal control, power signal feedback control. So here, if you see, I can go back to my previous slides. I'll show this diagram. Yeah. So if you see, this is the basic parts of a windmill. So you can see here blades, turbine blades, rotor, and mainly if you see there are RRB Vestas machine, we have the gearbox system. Some windmills we don't have any gearbox system. So here if you see the this is the actual diagram for this wind wind turbine. So here you have a generator, and this is anemometer used to measure the wind speed. So controller, gearbox, everything is there. This is a YAM motor to little bit twist the generator based upon the where we get more wind power. Okay, so this is the basic structure of the wind turbine. So the maximum power extracted will be 1 by 2 rho A V cube into Cp lambda comma B. So Cp is nothing but power coefficient or aerodynamic efficiency. So that is nothing but power output of wind turbine by power contained in the wind. And the lambda is nothing but tip speed ratio, speed of the tip to the wind velocity. Okay, so if you see my slides are can you see my slides?
Slides are visible, sir, but it's not moving. Now we are seeing your current slide.
Now you can see my slide.
Yes, sir.
Okay.
If press the arrow mark.
Oh, okay, now so we'll put in the slide. Now you can see, no?
Okay. Okay.
Yeah. So this I was explaining earlier that 4-quadrant operation of WFET induction generator. So the thing is that we have a gearbox. So gearbox, actually we have an optimal value of this wind speed where maximum power can be generated. So that is 3 to 15 meters per second. Wind velocity should be there. So this gearbox will increase the speed of the rotor so that more power can be generated once it is given to this rotor of the DFIG, and we will vary the pulses for a this is a back to back in the converter, so we will vary the pulses to get our maximum power. So there is previously they are using a permanent magnet synchronous generator. Okay, so if you see that advantage of if you see the advantages of PMSG, we have very high torque in compared to the other machine even at low speeds compared to induction motor. So that is why later they were using PMSG. But one drawback of this permanent magnet is that nowadays the getting permanent magnet, it is a little bit difficult because of this ban of China. We have banned the China products. So that is why we are going for other types of generators, like what I told, DFIG. So it is nothing but a slip ring induction motor where back to back converters are fed inside. Okay. One problem with this PMSG is the demagnetization of permanent magnet occurs due to overloading. So that is also important because magnetization, if you see once that it's aging, once it age, demagnetization occurs very easily. So it cannot hold overload, or it cannot hold the load for high power generation. So that is why that issue is there. So this is nothing but your optimal torque control. So if you see a control system, if you see more or less it is same. So inner, if you see a current control or torque control, outer will be a speed control. So we have a reference torque. Okay. So this is a wind energy system. This is for our analysis we can do. And if you see the mechanical torque in Newton meter and the generator speed, we will get this optimum torque value from this curve. So this is we have to do for different windmills, and we need to find out the optimum torque curve. Okay. This MPPT screen, that is maximum power point tracking. If you see, this is first diagram is the basic control diagram, see what we will do in a normal case, we will measure the voltage and the corresponding current, then we will be calculating the output power or sorry, input power, and we will see for every samples. So if the current sample value is more than the previous sample, then what we will do, we will try to increase the duty ratio, and then it is given back as a feedback. If the current power is less than the previous power, then we will complement it. That is, we will reverse the increase in the duty ratio, and then we will give it together. That is, if it is plus, then we will give you minus. That's the thing. So addition or decreasing in the duty ratio. So the problem here is that the regulatory issues are there. That is complexity of subsidiary structure. So complexity is more. Okay, and also land acquisition, that's a general thing. So lack of cooperation between the developers and purchase, that the issue is here. So the government must reevaluate the wind energy policies, and now they are doing a lot of policies they are changing so that more and more people can invest and they can purchase the power. Okay, so this is finally the fuel cell. So fuel cell, if you see, fuel cell, we are giving fuel in this fuel cell, and it is burned, and that amount of heat, so we are converting it as a power, and it is converted into DC is converted into AC power. Okay, so remaining thing is wasted, but wastage of heat, everything is there. So this is not best one, but nowadays they are using for like very heavy trucks and all. They are going for this fuel cells. So characteristics of fuel cell is that it has high efficiency and low emissions, continuous operation, and rapid refueling and high power density. So one drawback is it has a slow dynamic response. And if you see, this is also used in traction application. So in nowadays we are using this one in the EV application. Okay. So if you see the basic control, any control mechanism, if you see this is a current control loop. So here we have a compensator. So compensator, what we will do, this is the converter, boost converter. We will design the small signal modeling of this, and from there we will find out the small signal modeling of the boost converter. Then we will go for the Bode plot to find out this. From there we will find out the desired phase margin like 55 degree and desired gain margin is positive. So if it is not achieved, then we will use the compensator here, and then from the output of the compensator will be given to the pulse width modulator, and the PWM pulses will be adjusted. So this is the basic loop, closed loop we will be using in any DC-DC converters. So these are my references. So thank you. Thank you. Thank you, madam. Can you, madam, it's audible, no?
It's audible.
Sorry, actually there was some bandwidth issue was there. Yes, madam.
Yes, sir. That's the problem. So actually, if possible, please send the PPT, sir. I'll share with the participants.
Sure,
That's
madam.
a very
Sure,
nice
madam.
presentation. The only problem is that the PPT was not moving. That's the only problem, sir. But really,
because we have a lot of bandwidth issues are there. So like evening classes, other things. So that is the reason. I'm using my department system.
Okay. So short vote of thanks to you, sir. So on behalf of Nurul Islam Center for Higher Education, I extend my heartfelt gratitude to Dr. Arun Dominic, sir, for delivering an insightful and engaging session on emerging trends in renewable energy systems. His deep expertise in power electronics, electrical drives, and renewable energy solutions has provided us with a valuable understanding of the latest advancement in this critical field. Dear sir, we truly appreciate the time and effort you have taken and for being with us today and sharing your expertise. Thank you once again for your enlightening session and for contributing to our learning journey. So we look forward to more such interactions in the future. Thank you. Thank you very much, sir.
Thank you, madam. Thanks a
Yes.
lot for patiently hearing my session.
Okay. Thank you, sir. Dear participants, if you have any doubts, you can ask. Okay, sir. No problem. So please send us your PPT, sir.
Okay, madam. Sure, madam. I'll share it to you.
Okay, sir. Thank you very much, sir. Thank you.
Thank you.
So, dear participants, next session will be by 7:30. So once the expert is joining, I'll send the message. Thank you.
Hello.
Sir, good
Yeah.
evening, sir.
Good evening.
Yes.
Good evening,
Good
everyone.
evening. So shall we
Can you-
start the session, sir?
Yeah, we can start actually. So,
Okay.
should I start sharing my screen?
Yes, sir. Yes, sir.
Okay, give me a second.
Okay.
So everybody is joining online this session?
Yes, yes, sir. Yes, sir. Online only.
Okay, gotcha.
Okay, sir. So good evening, everyone. It's an absolute privilege to introduce today's distinguished speaker, Dr. Arul Subbiah, a highly accomplished IC design engineer with over 2 decades of experience in the semiconductor industry. He is currently serving as a principal IC design engineer at Broadcom in San Jose, California, United States, where he is responsible for designing critical modules in cutting-edge PCIe switches used in high-performance data centers. His expertise extends to multiple successful system-on-chip tape-outs, contributing to the development of next-generation semiconductor solutions. Dr. Arul Kumar has a profound understanding of chip design and verification with hands-on experience in system Verilog, universal verification methodology, application-specific integrated circuits, Perl scripting, and system-on-chip architectures. Throughout his career, he was worked extensively with high-speed interface protocols such as PCIe, USB, and MIPI, making a significant contribution to the advancement of semiconductor technology. Before joining Broadcom, he held key engineering positions at Arun Chip Systems, General Atomics, and WinChip Systems, where he played a crucial role in ASIC design, verification, and the development of industry-leading semiconductor products. His extensive experience in both front-end and back-end chip design process has made him a respected expert in the field. Dr. Arul Kumar holds a PhD in Electrical and Electronics Engineering from Santa Clara University, California, United States, where his research focused on error correction code using GPUs, a critical area in ensuring data integrity and reliability in computing systems. He also earned a master's degree from Southern Methodist University, Texas, United States, and a bachelor's degree in instrumentation and control from Satyabama Institute, India. Today, we have the privilege of gaining insights from his vast experience as he shares his expertise with us in this faculty development program. Dear sir, we extend a warm welcome to you as we are very eager to hear you.
Okay, yeah.
Welcome,
Thank
sir.
you very much for the long felicitation, and I really much appreciate it. Okay, so let me start sharing my screen. Okay, can you guys see my screen or not yet?
No, sir, not it, sir.
Okay.
So in the top, there's a button share.
Yeah, I'm trying to figure out. I know there is some. Okay, so I want to share presenter mode and then so I did change. Let me dial out and dial back in. Okay. Yeah.
Okay, sir. Okay.
Sorry about the delay. I'm trying to see. Okay, I want to share the window. So it's saying something about security and privacy settings, and it says I wanted to share, but it's saying recording has started, and then I've given permission, but it's not allowing me to share. Can you hear me? Hello?
Yes, sir, I can hear you, sir. We can hear you, we can see your face, but presentation is not visible.
Okay. It says go to security, screen recording to give permission and start sharing. And then I'm giving the permission, but it's not allowing me to share. Is there something at your end you have to do, or?
No, sir, actually, so once we are clicking the share, we'll be getting share content, screen, window, or tab.
Yes, it says it says share window. That's what I'm clicking. Okay. And then it says go to security and it says go to security, privacy, screen recording to give permission and start sharing. So I did give permission.
Choose what to, so we are not getting that thing, sir. So we are getting choose what to want to share. Entire screen, when you're clicking means you'll be getting the entire screen. That's all.
Okay. So if it doesn't work out, can you give me your email ID? I'll give you the PPT and you can bring it up and then I can work it.
Okay, sir.
Can you send me your email ID, please?
I'll send, sir. I'll send.
Let me email it to you. I'm sending it to you, Mary. Yeah. You know, like I'll try to figure out, what's happening here. I'll try it, but anyway, I sent the presentation to you.
Okay, sir.
Did you get it?
Here, sir. Yes, sir.
Okay. Yeah.
But I have you sent, sir? PPT?
Yes. It's marycynthia@gmail.com, right?
Sir. Sorry, sir. So Mary Cynthia. So another one mail, sir. I'll send. Mary Cynthia. Chennai Union. Sir, please send to this mail, sir. Mary Cynthia at chennaiuniv.com.
Okay. Mary. Okay. I'm sending it again.
Okay, sir.
For some reason, it's for security reason, it is saying I cannot share, but I don't know what's happening.
Sir.
Did you receive it, Mary? Okay, here we go. Finally, we got it, right? Okay, let me start. I know we're a little bit delayed, but yeah, so like Mary mentioned, right? So I'm Dr. Arul Subbiah. I'm an IC design engineer at Broadcom Limited, and I am also affiliated with Santa Clara University. Can you guys hear me? Hello? Hello? Mary, can you hear me? Okay.
Sir, I can hear you, but shall I start from another one? Because this is the main system. So 1 minute, sir.
Okay. Yeah.
Yes, sir, I can hear you. I'll start at share from another one system, sir.
Okay. Yeah, sure. Let me know when I should go, then I'll start speaking. Okay.
Okay, sir. Okay. Sir?
Yeah, shall we start?
Oh, yes, sir.
Oh,
Yes, sir.
yeah. Sorry about the delay.
Oh,
So,
thank you, sir.
it's, so my name is Dr. Arul Subbiah. I'm a IC design engineer at Broadcom Limited. I'm also affiliated with Santa Clara University, where I got my PhD from. Yeah, can we move to the next slide, please? Yes, so here is a brief outline for today's presentation. Um, can we go to the next slide, please? Yeah, so first I'll give an introduction about IC design. I know the topic is about power systems. So now the industry arena is completely changing. So there are a lot of AI systems. Now previously all the components used to be like separate elements, but now they are all packed into a single IC design. I'll show you what's going on there actually. And then there is a lot of emphasis on how to save power within a chip. That's the new trend with all the AI things that's going on. So personally, what do I do is like I work on chips that connects AI systems, and then also like work on a lot of the wireless system on chip chips also. So there is a lot of emphasis on power. How do you save power? Static power, dynamic power, and it goes on. So for today's outline, what I thought is a good idea is like, I'll walk you through an implementation of a VLSI implementation of circuits and how do we save powers and what do we do to save powers, and then also like GPU implementations, right? So I don't know if a lot of people have heard about this NVIDIA GPUs, Blackwell, Rockwell, and all those kind of systems. So how people code for those kind of a system keeping power in their mind, and then I'll briefly give you the conclusions like the industry trends and how things are moving. Okay, next slide, please. Yeah. So if you have any questions, please feel free to stop me or ask questions. I would really appreciate that. Okay. So GPUs, right? So GPUs are integrated with a system on chip for mobile and consumer electronic platforms. Please, next one, please. So keep pressing the tab, Mary, until this whole thing populates. That'll be easy. Then I can explain. Yeah. One more. Okay. Go back. Go back. Actually, go. No, no. We have to go back. Actually. No, we have to go back, Mary. I think maybe instead of the presentation mode, if you go press escape and then we can.
Yes, sir, such madam.
Yeah, that's the one. Yeah. Okay, got it. So these here in the picture, I have the third slide, right? So in the picture, I have depicted what the circuits look like within a chip, right? So the first one is an A7 processor, the left one, and then the right one is an A8 processor, and the bottom left is a Snapdragon, that's another chip, and the right one is the Maxwell. So Maxwell is one of the early version of the AI chips that NVIDIA did it, and this A7 and A8 chip are the chips from Apple. So you guys know that Intel used to be the pioneer in the processor like x86 and then so on. But now the trend is a lot of these software companies, they do their own processor, right? So instead of saying processor, the right term to use is called SoC, system on chip. Why they call it a system on chip is that you borrow all the components and then you populate into a single die. Like for example here, right, on the A7 processor, you'll be having like 4 GPUs actually. So the GPUs are the one which you use to display your display screen in your iPhone, and then they'll have also like ARM processors in it. So it's a RISC-based processor, and then they'll have memories inside, and then the components, how do you communicate with the other chips within your iPhone. So they're all packed into a single SoC chip. Now, how do you save power within this chip, right? So that's where the new trend is. Like, when you have components externally, you can have switches, regulators, and then, you can turn off your some of your switches and then save power. But when it is all packed into a single IC design, then saving power, they have different techniques. Okay, so the point I wanted to show here is, all the components that you used to see it on a motherboard as a discrete components, they are packed into a single die, right? And the consumption of power is so high here. Even a single chip could be like, consuming more than 100 watts. So we have to be very careful about, how we save power, and then, how do we save on static and dynamic powers. Okay. And then for the GPUs, right? So GPUs, um, they use CUDA software actually. I don't know if you guys are aware of it. So CUDA is kind of like a C compiler, but that's been done by NVIDIA. So they have their own proprietary version of compiling to their GPUs, and that's where a lot of your AI programmings are done these days. Okay, there are also competitive softwares like OpenGL and OpenCL, but they are not very efficient. Okay, please go to the next slide, please. Yeah. Next slide. Okay. 4. Slide number 4. Yeah, okay. So here the other thing that I want to show is storage actually. So for all the systems that you have, either you have AI systems, or you have your phones, storage is a very important element, right? So this is one example of a flash memory. So here also the power consumption is a big factor. So what happens is that instead of a hard drive, hard drive used to consume more power because you have to spin the wheels, and then you have to read it. So every time when you read, there are mechanical devices that needs to turn on, so that consumes more power. But the newer generations, they use solid state drives. The reason why is reason is, one is quicker, and the second reason is why is because it consumes less power. So you see a typical element here, right? So we have a p-type silicon substrate, and then we have a gate element in between, and there is a storage in between that actually. So the way it stores is that, the populator voltage into it, it stores that voltage, and that's it. You never turn on the circuit. So whenever you need it, when you want to read it, then when you access this particular cell, what happens is, only during that time you turn on the gate and read it. On the other time, it is all settled down actually. So usually it is like a 1 bit they store in these gates, or it is 2 bit, it depending on the voltage level. So they call it less single level cell, or like multi-level cells, so MLC. So what happens is, how you can differentiate the voltages that's stored inside your cell. If you're able to segregate them into 4 different voltage levels, then you could store 2 bits per cell. If you can only segregate 2 bits, I mean 2 information, either 1 or 0, then they call it as a single level cells, right? But these are prone to a lot of errors actually. So that was my research thesis actually. Like, how do you do the error correction? Because there are techniques, how to do this error correction within the storage cells, and that was part of my PhD thesis. I spent a lot of time refining these algorithms on GPUs and VLSI implementation. So yeah, please go to the next slide, please. Yeah, okay. So here is how the storage will look like. So it'll be usually like 4 kilobytes or 4K bytes per block actually. That's how people store, and all the SSDs in your GPUs or in your iPhones or hard drives or even laptops. So it is 4 kilobytes. Please go to the next slides. Yeah. Okay. So here is one example of how you read from the flash memory, right? So when you access to these storage devices, right? So when you run something on a chip on your phone or anything, sometimes you want to save your file, and that file will be written into these storage devices. And this is how typically this is a timing diagram actually, like how it works. So basically what we are here, what it does is that there is a clock signal, and it's a 125 megahertz DDR. DDR means it's a double data rate, so which means you use both the positive edge as well as the negative edge of your clock to transfer data. And then there will be a protocol, right? And the data is like only 1 byte wide. And then if you want to do a typical let's say like a 4K page, your transfer might take around like 100 microsecond to transfer these 4 kilobytes information of data. The reason is so the where does the design challenge comes from is that when the activity is not there and you don't read anything from these storage devices, how do you save power, right? Because there is no clock. Then then what you can do is like you can shut down some of your circuits within your storage element to store power. And especially they do a lot in mobile devices, because we need to save the battery power. So they write protocols uh, to save power in their mind. Okay, so that's why they stop the clock, and then they have additional signals like the chip latch enable, and all those signals that gives an indication to these SSD device to turn off their power. And then they also give a lot of latency time for the storage devices to turn on themselves in the event of a wake. And once they wake, there is an initial latency, and after the initial latency, then you can do a big file transfer. Okay. The next slide, please. Okay, so power saving, right? So now how do we, like, because there are a lot of SSD drives, across the industry, how do we save power, right? And how do we coordinate, multiple people or, multiple vendors together, right? So the first way is, they define interfaces, industry standard interfaces, like for solid state drives, like for example, ONFI, right? It's an interface that the whole industry agrees, and that's the most popular one that everybody uses. That's the timing diagram that I was explaining before, right? So where you have a clock signal, you have a latch signal, and all the control signals that gives indication or clues how to save power to the device as well as the host side, right? And there are also like other interfaces like Easy NAND, and then there are custom interface like Samsung, or some memory vendors like Micron. They define their own interfaces, but if you want to work with them, you have to have their own custom memory interface, right? And there are also other standard interfaces which are primarily used for not just for storage but for other connectivity too, like SDIO, USB, PCIe, SATA. So these are, they call it as IO protocols. So IO protocol is they are not geared towards a particular what do you say, like particular devices. So PCIe will be like a general connectivity. The PCIe, they use it in AI platforms, they use it in mobile platform. So these industries, they provide protocols to save power. Okay. Next one, please. Okay. So now I'll go into a details of a VLSI implementation for one of the BCH codes, and we'll walk you through how do we, like, take a how do you how do you convert an idea into a design, and then how do you save power once you have changed your idea into design. How do you save power? How do you optimize it? That's where the real challenge comes, and where the uniqueness come from. Okay, next slide, please. Okay, so here is some basic math. So for the BCH codes, right? BCH is an error correction code. So some basic math here. So they work on a finite field. So these finite field, I mean, if you're familiar with abstract algebra, this is part of that mathematical field where they have a defined, like you have a real domain. There is also a finite field mathematics. So this was invented by French mathematicians called Galois. So it's like a polynomial equations where each one of the variables have a roots in the finite field, as well as the coefficients. They will also belong to a Galois field. So most of the cryptography, or if you look at error correction codes, they all use Galois field math. So in this example, so we use a finite field mathematics, and we will use a Galois field of 2, and then in a different dimension, like 2 to the power m dimensions, right? So that's the information that I want to show in this particular one. Can we go to the next one? Next slide, please. Yeah, I know this might be a little bit abstract and daunting for some people. So here what I'm trying to show here is how in a mathematical world how the problem is visualized, right? So we have a Galois field, and then this is 2 to the power 3, so that means it's a dimension of 3. And then how do you represent it? There is a top table that tells you what are the roots of this polynomial equations, right? So there is an imaginary root called alpha, and then in finite field they are the powers of these alpha, this imaginary root. So alpha to the power 0, alpha to the power 1, alpha to the power 2. And then how do you represent it in the binary field, right? So that's the bottom one, right? So in the mathematical world, it will be more abstract, but when you go to the binary, it becomes very easy. But it might not be like a counter that we are used to. Usually the counters go like for a binary representation, it goes from 0 0 0 0 1, then it goes to 2 3, and then 7. It goes in an ascending order, right? But the math doesn't work in a finite field like that. If you pay close attention, you'll see that the first element is 0, the second element is 1, the third element is 2, the fourth element is 4, and the fifth element is 0 1 1, and then it goes to 1 1 0, right? So it will be jumbled, and there is a algorithm how to achieve this. So that will be defined by the primitive element, the primitive polynomial that we use to construct this particular field. Please go to the next slide. Yeah, so once we have yes, so once we have established the finite element fields, then there are multiple codes that they use. Like I said, like Reed Solomon, there is BCH code, and there are a lot of numerous cyclic codes that they use, right? So BCH is one of the easier version, or next to Hamming codes. So BCH is invented by Bose, Chowdhury, Hackenham. So they invented this particular error correction code. And what it does is that they create a block size for the 2 to the power m, and then they also have a parity bits to it. So the parity bits, the redundant information is part of the parity bits. So the number of parity bits that we need to have is m times t. And then for the BCH code, the bottom one, you can see that the number of useful fields, the 8192 is the useful fields, and then no, sorry, the whole field, and then 80, 87 is the useful bits, and the rest of the bits are all parity. In this particular example, so we are doing a Galois field of 2 to the power 13, right? So 2 to the power 13 is like a 13 dimension of the finite field. Okay, next slide, please. Okay, so now we'll get to the interesting part. Yeah, so here this shows, like, how we do the g of x, which is called the generator polynomial, right? So generator polynomial, is mathematically we take four different equations, or depending on 2t error corrections, and then we look at those minimal polynomial, and then multiply them, and then you find the least common multiplier, and it will give you an equation, right? But the key point from the slide is, when we design these kind of designs for a BCH decoder, there are three engines to it. One is the first one is to generate the syndrome, and then the next one is to generate the key equation, and then the last one is to find the roots of the key equation. Okay, next slide, please. Okay, so here is a VLSI implementation. So now, till now it was like, math and understanding the concepts. When it comes to implementation, then we have to find out, how do we design the multipliers, right? Multipliers for these kind of circuits, right? And then there are different multiplier techniques. One is the standard basis multipliers. How do we do the multipliers in a Galois field? So this is primarily easy, like, the way we do a multiplication in a real domain, or like, what do you say, like in an integer domain. It is very similar to that. And then there is a normal basis multiplier too, actually. So what happens is that you multiply it as part of the basis, and then you need to find the roots, and then you add the roots, and then to take the inverse back again, right? And there are also like dual basis multipliers. So dual basis multipliers is like, how we like, we know there is an imaginary element called alpha, or the roots called alpha. You could also represent it as another one, where you say the imaginary element is beta, another version, and then it's an isomorphic thing. Those two circuits will be the same, but it's just that you are representing with a different basis, right? And there is a simple lookup table approach, right? So these are the options as a designer you will have, like, how do you want to design it, right? So now what we need to think is, which the whole goal in designing is that you want to have less area, you want to have less power, and then you want to have it quicker. So if you can solve this problem, which will suit your needs, that's what people used to go. And then the standard basis multiplier is a good method to say, you have a low area count, and then you can also do it faster and with some power, right? So if you go to the lookup table type of approach, it's going to take more time, because every time it's a RAM you read, it's going to take 2 clock cycle for you to just to do the multiplication. It takes more time. You guys are able to hear me, right? I keep on talking.
Yes, sir. We can hear, sir.
Okay. Yeah, if it's too much, or give me feedback, if you want to stop, and any clarification, I'll be happy to help. Yeah.
Okay, sir. Okay.
Okay, yeah, please go to the next slide, please. Yeah, so here is a VLSI implementation of a encoder. Actually, you'll see some circuits here. So here what we are trying to do is this m of x n minus k, the remainder of m of k x n minus k is nothing but it's a mod operations. You can say it is a kind of like a reminder, right? The easiest analogy is, let's say you take a number 20, and then you want to divide by the number 3, right? So 20 divided by 3 is 18. You get a remainder of 2. That's all this circuit is trying to do, but in a finite field, right? And there are two versions of doing it. One is you do it in the z domain, and the other one is in the normal x domain, right? So the same circuitry in two different forms. Okay, can we go to the next slide, please? Okay, so here is a circuit for the syndrome generator. So what? No, this is an encoder actually. So this encoder, what it is trying to do is, we are feeding in the polynomial m of x, and then you keep shifting it. So what happens is that, let's say you have 4 kilobytes of data, you will flush through the circuit like, 4 kilobyte times. And then at the end of it, you will get the syndrome or even the encoder also. You can use for both. So what will happen is that, at the end, like we are reading from the storage drive, you're feeding into the circuit, and at the end of the last byte that you fed in, you will get the encoded value or the syndrome for it. So that's all the circuit is trying to say. And wherever you see that X mark, that's a multiplier. And then wherever you see that plus, a circle with a plus, it's a addition. But remember, this is a Galois field addition and Galois field multiplication. This will not look like a circuit that we usually design for our normal multiplication and the normal divider, right? Also the normal addition. Can you go to the next slide, please? Okay. So here is the top level view of the decoder. Like I said, so these will be constituting of three modules, right? One is a syndrome generator, then there will be a key equation solver and an error corrector. So these are all circuits. The rectangle diagrams that I have shown here, these will contain all the Galois field math, multipliers, division, and all those modules. And then we call this whole unit as a decoder. Right? The first will be the syndrome generator circuit. The next will be the key equation circuits. And the third one will be the error corrector circuit, right? So these three modules will be the circuits sitting in your chip. Now the whole challenge would be like, I have this circuit here. This circuit will not turn on all the time. Now I don't need to do the error correction all the time. And what do I do, right? How do we save power? Those things I'll talk about it later. But first, let's go through the circuits here. Can you go to the next slide, please? Yeah. So this one is the syndrome generator. The next one. So I'm giving a logical view of it. This is a polynomial. So when you are feeding in the circuit, what we are really doing is you take that 8-bit of value or a byte, and then you're basically plugging into the x variable. That's all we are trying to do. And then there is an addition to it and a multiplication to it. We aggregate them, and then that becomes the SJ syndrome, right? So this circuit, you keep on feeding your 4 kilobytes of data to figure out what's the data that's going to come out of it, actually, syndrome generator, right? And this will be something very easy to compute. Syndrome is much easier to compute. And the mathematical representation is, the R of x is the receive channel, and the mod GIFX. GIFX is the generator polynomial of your BCH code. Okay, the next one, please. Okay, so this will be a little bit of a complex circuit. So what happens here is there is an algorithm called Berlekamp-Macy algorithm. There are multiple algorithms, but I won't go through all of them. So the Berlekamp-Macy algorithm is where what you do is you iterate the circuit for the 2t number of times, and then you will find out, at the end of this, you will get a key equation. So this whole circuit, what it is doing is that if you run the circuit, you take from the syndrome generator, you give it to this circuit, and then this runs for example, let's say you want to do 12-bit error correction. You run the circuit for 24 clock cycles. At the end of the 24 clock cycle, you will get a key equation. So that will be the equation that holds the information of where the error is, right? Please go to the next one. Okay. So here, once you get the key equation, all we are trying to do is we will plug in that different elements or the finite feed elements to this circuits, and then we figure out which location had the error. All the circuit here is what it is trying to do is it's finding out if there is an error there or not. If there is an error, then you flip the bit. So if you look at it from a top level perspective, you have your iPhone, you have a solid state drive, which is also a storage device in your phone. And all this this circuit that we are trying to put here is that it is bound that a lot of the information that you store in the solid state drive within your phone will have errors. So the probability of error is like 10 to the power minus 8, or sometimes it will be like 10 to the power minus 6 bit error rate too. So these circuits are sitting in your chip, and whenever there is an error, these circuits are turned on, and then they correct the errors, and then they give you the right data. And then once they know there is an error, then the system, what do they do is they go take the data from that particular block and then rewrite it back again to correct the errors. So that's how it works. I mean, for the user, they have no idea that these circuits are working in parallel and correcting things and so on, right? And that's why a lot of people are moving towards the cloud. The reason why is the solid state drives, after 4 or 5 years, they don't have a warranty. Like, after 10 years, the SSD might go away, or, you might lose your information. And that's why there is a heavy push to put it in the cloud, because in the cloud, they have similar circuits like this. And what do they do in the cloud is that they keep updating the solid state drives, or even like a hard drives. They keep changing that information, and there is a lot of redundancy, so your information is stored. So if you have any like USB drives with SSD or anything, after 10 years, you might not be guaranteed that you will have all the information there. You might lose those information, even a pen drive and all those things, right? Because of this errors, actually, because it's more prone to errors, and you might lose those information. Okay. Next slide, please. Yeah. Yeah, okay. So here is a timing diagram, like how the data flows in through. So the data, there is in the middle of it, you will see the data 15 down to 0. So that's where the data has been read. And then if you detect an error, it flags there is an error. Only if there is a detection of error, then we turn on the circuits. If there is no detection of error, we don't turn on the receiver circuits or the decoder circuits. So that's where we save power, because you're going to read this every clock cycle. So this power is not something that you turn on and off like in a second or 2 seconds. People are so clever that even within microseconds, they want to turn on and off these circuits to save power, because the battery power is very important for us. You want to save the battery power as much as we can. And people are like Apple, or like Qualcomm, they push the limits. Like every year, I mean the spec goes down such that even though they're able to charge more power into the battery, but it's not keeping up with the design. So there is a huge push on the design to save power when we don't turn on the circuits. That's the best way to save power. Okay. Next circuit. Next one, please. Okay, so here is a VLSI implementation, right? A simple way of doing saving power is that, you would see on the left hand side, right? So it's a flip-flop, and you have a mux and you have an enable, right? So if you have these kind of circuits, what will happen is that the clock going to the flip-flop will be always be turned on. So there'll be like a lot of dynamic power going on to these flops. So what will happen is that this flops, even though you are not giving the data, these flops will consume power. Okay. So the one way to change it is you can, instead of giving the enable to the data, you can give the enable to the clock. So which means you stop the clock. We basically stop the clock when it is not enabled. So what does it mean actually? So that means, all the power, the switching circuits, right? So they'll be turned off and you will have less power consumed by the flip-flops. And if you look at our circuits, right, there will be like billions of flip-flops like this. So, but the flip side of it is that, the clock gating circuits that we put in on a clock, they are very tricky circuits, meeting time. And then if you want to go production, there are like, different corners. So that's the biggest challenge that we face when we use these type of approaches. But, and there will be like these have to run at a higher frequency. Let's say, you want to run at 1 gigahertz. And these type of circuits, when you use clock gating, it will affect your timing. So, you have to think about, how we can optimize the timing there. So that's the challenge. So this is the best method that we can use it to save power. Okay. Can we go to the next slide, please? Yeah. Okay. So here is like at a global level, right? So what happens is that there are a lot of small modules within the system on chip. If you remember from my the very initial introduction, you'll have like GPUs and a lot of the bigger components within the chip. And how do we save power is we put them into different switches for the VDD rail. And we have switches. These switches are within the chip. These are not switches external to the chip. These are internal to the chip. And what we do is we turn off the VDD power to a particular module. Like for example, let's say this ECC code, right? If the user is not using, or he's not browsing anything on his phone to get the data from the SSD drives, then the best way to save power is cut off the VDD, right? Because we know that the user, the iPhone is switched off, so we want to turn it off. So the way we do it is for this SSD drives where we have decode engine, they'll be in a different power domain, and then there will be a power domain switches here. So there will be some of them we call it as always on domain. So this always on domain looks at all the domains which are not of use, and each one of them will have a switching circuitry on the VDD, and then we turn off the power, right? But when we turn off the power, what happens is that there is a new challenge coming in, because the circuit that's feeding the gates will become open drain or will be a high impedance to those gates. And in typical design, like a decade ago, like 10 years ago, we there used to be like an industry norm that we should never give a open high impedance or an open drain circuit towards the gate, because that might burn the chip. That used to be one of our checks that we used to do. But after this mobile era, what happened is that people wanted to save power, so they the foundry used to like started designing special cells that they call it as the isolation cell. This isolation cell can also take in an open drain or a high impedance, like on the gate, the AND gate that you see. One of the input will be a high impedance or an open drain, but the ISO that represents the isolation. So if you turn on the isolation, then they will get off the open drain, and then anything that goes out of the AND gate, you will still get the proper voltage. It is 0 or 1, depending on what you want to isolate. Now, always some of the typical ones are always the output is 0. Some of them will be active high, in which case we have to invert it again and then use 1. So what do we do is, if the error correction code, you don't want that circuit to be turned on, first we turn on the isolation cell. So you isolate from the circuits that will be like feeding into the next domain. So this domain, it's you are getting the voltage, and on the other one, the decoder circuit that we have, we turn off the switch. So this is the best way to save power, because there will not be any leakage power, there will not be any dynamic power. All the all the thing that you will have is that the isolation cell, that will be getting the power. Imagine on the SoC, when you don't use your iPhone, you don't want your GPUs, you don't want your ARM processor to run all those. So they all will be in a power island. Actually, we call it as power island. So all this power island, what we do is turn off these powers. What is the flip side of it, right? But when you wanted to turn it on, it's like it won't come in quick. But the I mean, in the previous thing, what happens is that it takes a very long time to switch. So it takes like milliseconds, or sometimes even like seconds to turn it on. Some of the low end phones, it takes a long time to turn it on, right? But that's where the challenge will come in. How do we turn on the switches much faster? How do we get back to the working conditions? The other option is, you turn on some of the power islands, and then which the user could use, and then you turn on the other islands in the background, so the user doesn't have to wait for all the circuits to be turned on, and you turn it on need basis, right? Next slide, please. So that's how we save power on the VLSI side of it. So now I'll give some kind of an insight to the GPUs. Yeah. Next slide, please. Yeah. Okay. For the GPUs, right? So GPUs is the latest trend and the hot topic that the whole world is looking. And then a lot of AI machines, they all use these circuits actually. And in fact, a lot of these circuits, this particular circuit that I'm showing you here is for a Maxwell. And then this is an NVIDIA GPU. This is Kepler and Maxwell architecture. So there is a multitude of streaming that happens here. Okay. So there are 32 cores per streaming multi-core. So that means you think of it like, there are 32 processes sitting inside here, which are multi-threaded. This is only one single die. And then what people used to do, even within a board, they will have multiple of these chips also. Okay. And then what do they do is, the whole idea is you're writing algorithms to keep all this processor active. So in the VLSI, we used to turn off all the power. GPUs, we don't turn off all the power. What happens is that they always consume power. And then you write algorithms such that you don't peak your memory. So here, how to save power is your real how you write your code, rather than how to save power in each one of the cores. I mean, we are not there yet. That is, there are a lot of research going on over there. But a lot of these AI systems right now, they don't really care about much of the power. All they care about is the peak power that they use. And how do you control this peak power is by your algorithm. How do you use this course efficiently? That's how you use it actually. So what happens here is, when you write your code, the code goes to multiple of these code. So sometimes they call it as SIMD or MIMD. So SIMD is like single instruction but multiple data. So all these cores, they will have the same instruction going in, but they work on multiple data. And in MIMD, it's like multiple instruction, multiple data. So what it means is that, each core could be running different instruction, but it might be targeting different data. But the challenge there is, the synchronizing the cores between them, that requires a lot of handshakes. Okay, can we move to the next slide, please? Okay, so here, we have these cores, some into a streaming core actually. So here what we have is that you see wherever you see the core here, so the core is where your RISC processor is, right? So these are the tiles of RISC processor, and then you will have the registers. The registers are the L1 cache that the processor can access. They will also have L2 cache, but that will be outside of this module. That L2 cache could be like shared across multiple streaming multiprocessor. And then they'll also have pipeline circuitry here, and then also they have some other engine to help the warp, actually to help the CUDA software. The CUDA is the software that they use for NVIDIA GPUs. You can't use the CUDA on other GPUs. You can use it for like A7 GPUs, but they are tailored towards the NVIDIA GPUs, and that gives the most optimal compilation for NVIDIA GPUs. Okay. So the maximum thread that you can use is 1024 threads, and then they have multiple dimensions of these threads, which they call it as blocks. So you can basically, for a single core or single SM, you can have a dimension of 64 times 1024 times 1024 uh, real threads going on. So these are like multi-dimension. So that's how they are able to run these AI algorithms, because for each core, imagine you can give this much amount of jobs, and the real physical engine will be like 32, but there will be 1024 threads. The threads, what the thread does is that they are trying to do um, there are pipelines within the circuits. They are trying to keep the pipelines active as much as possible when you have multiple threads. When you have multiple blocks, is you are really not using the engine, but it's a way that the software guys make happy that they'll be running these in a threaded fashion. Let me put it that way. Okay, next slide, please. Yeah, okay. So here is a flow chart, right? So a typical flow chart, what are the memories used? What we use here, the host memory and then device global memory. So the device global memory is a memory that resides within the GPUs, right? And there is a lookup table, like in this particular case, we can't use the standard multipliers. We used to use a lookup table type of approach in GPUs, and then the power will be to the standard basis, and this is a flow chart of how we do the algorithms, right? Here the important factor is the kernel. So the instead of a C program, this will be like a kernels actually in CUDA. So this kernel is the one which launches everything in parallel. So we do a peak power at one particular time, and then you run it on parallel processor, you get the data, and then you basically cool it down. So that's how we save power. If you don't use your kernel to use this MIMD, what happens is that you will still have the GPUs. If your algorithm is not optimized, you are wasting power, just running because your algorithm is not optimized. You will be running the GPUs because we have to turn on the GPUs for this particular algorithm, and then it might take a very long time to do, and you will waste a lot of dynamic power. Okay, next slide, please. Yeah, so here is the pseudo code actually, how the code will look like in a CUDA software. How do we use the kernel codes, right? The syndrome generator uses a kernel code, the chain search, will be yeah, chain search also uses the kernel actually. So it is deploying. Basically, it's a single code. We are the bit position. Pay attention to the bit position, right, and BL position. So basically, what we are doing is we are launching multiple codes. We are giving each core a bit position and a block position. Imagine if you have 4 kilobytes, right? All we are trying to do is 4k times 8. So we are that many threads we are giving it in, and then we are giving to those engines. Though they all will work in parallel, and then we will collect the information back in. So which means you divided your job between 4k times 8 threads, and then you get it back. So you might even get the result back in 10 microseconds, right? So now, so that's how we are able to, like, when you do this AI thing, this the syndrome not the syndrome generator, the kernels, right? The kernels and the CUDA is where your power comes from. When you do AI algorithms too, they'll do all this parallel algorithms to search, to compute, complex statistics. Everything will go like this, and then that's how we are able to get the data back within seconds with this powerful engines. Okay, next one, please. Okay, so here is one of the research, I mean, the results are the board that I use for my research. So this one was with Kepler architecture. Sorry, yeah, no, the setup one was with my PC, and setup two is with the board that you see here, right? So this is a AI, we can say GPU. It could be also be used for low-end AI calculations. So it's a Jetson TX1. It has 4 ARM processor in it, and then you'll see that everything, you have a heating or like a fan to cool it down, right? Even though this is like a lower one, it burns that much power. We have to cool it, have a air cooling system to cool it. Okay, and then it has all the Wi-Fi and all the other connectivity. Next slide, please. Okay, so here is a graph, how the GPU gives the results, right? You would see that within like 1 millisecond, even for a 512 byte block, right, we're able to get the results within the left one scale is microseconds, so around like 1000 microseconds is like 1 millisecond. Imagine when within 1 millisecond you are able to solve problems for like what do you say, like 4 kilobytes of information. You're correcting that much error in that much amount of time. So that's the point I want to show here. And then after that will be our conclusions. Can we go to the next slide, please? Okay. So what is it? The dynamic power saving is huge in IC design. So we looked at the IC design, right? So the dynamic power saving is that, when you use circuits, we want to save the power when you provide the clock to the circuits, right? So the clock gating, right? So the clock gating gives the best saving. So basically, even if your circuit is running, and then if you gate the clock using your enable, that gives you the best saving, right? And the best saving is your power island actually. So if all the circuits you put them in, and then whenever you don't want to use them, you turn off the switch, and then you turn off those entire circuits. That gives you the best power saving, because you will also save the leakage power, right? And for the GPU codes, for GPGPU type of systems, you have to change your algorithm with power in your mind, right? Because these guys consume like hundreds and hundreds of watts of power. So you have to be very clever in writing algorithms. So the best algorithms which consumes less power, they will be the winner, and that gets deployed, right? For GPU type of this one. And then coding style for GPUs, right? So like I said, so the how you come up with the algorithms, how do you do that? That's how you save power for this power hungry machines. So I hope this session was informative. So these are like the late trends, you know. These techniques people use for AI type of applications and in a mobile. And you know, power is no longer, you know, some circuitry which is outside the design or outside the chip, and then you know you turn on and off the power. When the industry has moved, and then we even think about power saving inside the chip in GPUs algorithms, and that's how we are saving powers for the new generations. So with that, I would like to open the floor for any questions, any feedback.
Dear participants, so you can unmute your mic and you can ask your questions. Okay, sir.
Yes.
So thank you very much, sir. They have put in the chat box. They are thanking you for your informative
Okay.
speech.
Yeah,
Okay,
sure.
okay,
Thank you.
Okay, sir.
Thank you. It's a
So,
privilege to give info and you know, give some insights to the latest technology to you guys. Hope it was very informational.
thank you, sir. So on behalf of Noor Lusam Center for Education, I would like to extend my heartfelt gratitude to Dr. Arul Kumar for taking the time to share his invaluable knowledge and insights with us today. His expertise in IC design, semiconductor technology, and advanced verification methodologies has truly enriched our understanding of this ever-evolving field. Sir, your presence here today has been a great privilege for all of us. We sincerely thank you for your willingness to share your years of experience and industry wisdom with us. We hope to have more opportunities to learn you from in the future. Thank you. Thank you very much, sir.
Yeah, thank you very much. Have a wonderful day. Yeah. Bye for now.
Thank you, sir.
Sure, bye.
Bye, sir. Thank you, sir. Bye.